In our first example of a vertically submerged plate, I wanted to have us take a look at the same plate that we had just a moment ago, but I am going to change things up a little bit. We still have a 2 meter by 4 meter plate. It is going to be submerged to a depth of 9 meters. However, that 9 meters is going to be the bottom of where the plate is, and it's going to extend 2 more meters up in the upward direction. So the top of the plate will be at a depth of 7 meters. Now, as I mentioned before in our previous video, the hydrostatic force that is going to be felt by this is going to be the definite integral from a to b of rho times g times the depth as a function of x times the length as a function of x times dx. Now, I had also mentioned that the depth as a function of x is really up to us as far as what we want to do with it. So we're actually going to try this one a couple different ways. So for method number one, we're just going to define the surface of the water to be x equals 0, and we are going to define the downward direction to be the direction of increasing x. So as x increases, the depth is going to increase as well. So for this one, depth as a function of x is simply going to be x. Now, regardless of that, if we were to slice this up into a bunch of little tiny rectangles, you'll notice that the lengths of all of those little tiny rectangles are all the same. And it's going to be this nice uniform length of 4 meters. So length is going to be 4 regardless of anything. Now, as we're integrating, you'll notice that this plate isn't defined until we get to a depth of 7 meters, and it continues to be defined until we get to a depth of 9 meters. So the closed interval from A to B is going to be from a depth of 7 to a depth of 9. As such, we can set up the integral in the following fashion. This will be the definite integral from 7 to 9 of rho times g times the depth times the length dx. Now, when we simplify this, taking 1,000 times 9.8 times 4, and use the calculator to help me out here, I am getting 39,200 times x dx. Integrating this isn't too bad. According to the power rule, this is going to be 19,600 x squared going from 7 to 9, also known as 19,600 times 9 squared minus 7 squared. 9 squared minus 7 squared winds up being 32, and multiplying gives us a total of 627,200. And again, that would be newtons. According to our other method that we used for this, we came up with just over 705,000 newtons. This one is lower because parts of the plate are not at the same deep depth that this one was. They're a little bit higher, so that's why the overall hydrostatic force is a little bit less. Now, to demonstrate another method, I wanted to this time define x equals 0 to actually be the top of the plate. So this was method number 1. This will be method number 2. So for method number 2, starts out the same way. F is going to go from A to B of rho times g times depth as a function of x times length as a function of x times dx. Now this time, when we're at x equals 0, we are already at a depth of 7, which is why the depth is going to be defined as x plus 7. That way, when I plug in x equals 0, we'll get a depth of 7, and for every 1 that x increases, d will increase by 1 as well. The length still continues to be a nice consistent 4 all the way across, and this time the interval from A to B is this time going to go from x equals 0, the top of the plate, to the bottom of the plate, which would be x equals 2, due to the fact that the plate is 2 meters tall in this case. So with all of that in mind, we can set this up now as the definite integral from 0 to 2. One big advantage that we get out of defining x equals 0 to be the top of the plate is this lower bound of 2. That's really handy for us. Rho will be 1,000, g will be 9.8. Depth we have determined to be x plus 7. Length is that nice consistent 4 that we mentioned, and dx continues to be dx. Now we already know from our last experience that this is going to wind up being 39,200 once I multiply the 1,000 by the 9.8 by the 4. However, to get this into an integrable fashion, this will be 39,200 times the quantity x plus 7. So we'll go ahead and distribute that. Hey calculator, what's 39,200 multiplied by 7? Of course, if you wanted to, you could do something like a u substitution for this integral to avoid having to do such messy numbers, but what the heck, we're warriors, let's make it happen. Actually, integrating both of these gives us 19,600 times x squared plus 274,400 times x, going from lower bound 0 to upper bound 2. Good news is that the lower bound of 0 is just going to give us a lot of 0. As such, we're going to see 19,600 multiplied by 2 squared plus 274,400 multiplied by 2 minus, plugging in our lower bound will give us a lot of 0. Turning to the calculator to help us out with this massive calculation that we see here, 19,600 multiplied by 2 squared plus 274,400 times 2. What an amazing coincidence. We wind up getting literally exact same result as what we got the other method. No, this is not surprising at all. This is just a different setup for the exact same problem. So, as such, that will be how we get our hydrostatic force.